So good morning. Now, today we examine some application and design examples of, or at least the first steps, because we will see that the complete design of the controller is quite complicated, it's quite complex. So it requires different steps, different phases of work. Then we, as a first part of this lecture, we take into account the recursive estimation for linear varying parameters of dynamic processes, and it's something that it was already examined in the course of supervision and adaptive systems, but with application with for fault diagnosis. So it was a different application, but the tools are the same. So I'm going to download the first is the function recursively square with the forgetting factor, with this, which is the function, the basic function for recursive least square estimation with the forgetting factor parameter, and then a script file which is used for for displaying the results, which is named example recursively square switching model. So it's the second, and the third file is the generation of the parameter change, so the data with the parameter change, and the comparison, so is called the parameter change for FDI comparison. So under the assumption that the parameters are changing, so is explained, is shown how to use it. So let's go to with these four files and going to examine. So let's check the first file. So the first is I downloaded these four files. So let's check the first one, which is the function which is used for estimating the parameters. I just want to explain how to use. Is like in highlight with the main points. So you need to include to feed the input and the output. They are organized for because this approach can be used for single output, multiple inputs. So the matrix that you are using or passing to the function is organized. The first column contains the samples of the output, and the remaining ones are the inputs. So you know how, in this way, you know that you have at least one column, which is the output, and the remaining ones are for the inputs. So you can have one input or multiple inputs. But again, we are assuming that we are working with just one output, it's simpler. So, and as you can see here from the comment of the function, so it implements a recursively square algorithm with forgetting factor. So you are assuming that the order is known. So the order means, if you remember, the number of regressors, of how many samples are you using in the matrix phi, and the matrix yu contains the output vector followed by the column vectors of the inputs, if present, because this function works also for example, autoregressive models, so without inputs. And the function, just normally, we need also, if you remember, the order of the outputs follows the importance of the outputs if you need. So the first output that you need when you are estimating the parameter is the parameter vector. The second output that you may need is the estimation of your output, and you have also the matrix with the errors of your parameters, if you need. So the order, if you remember, the order of the outputs represents also the importance of the outputs that you may need for your application. And after some, I don't want to enter into the details, but if you remember, so it's a recursively square, so it implements a first part of the function, it organizes the inputs. So if you check here, it works with one output, so it means it's an AR model, or in case of single input is a CISO model, or a multiple input single out. And here you can, I don't know if you remember, is just the generation of the adaptive law for the estimation. So here you can recognize the adaptation of the parameter and the correction. So you have the gain. The gain is computed, if you remember, as the multiplication, as the product of the matrix, the covariance matrix, and the vector of the regressors. And if you notice here, PT is multiplied by 1 divided by the forgetting factor. So lambda is one of the input parameters for the function. And just as a comment, if the number, because in MATLAB you can design functions with a variable number of input parameters. If you pass less than 3 parameters, it assumes that a lambda is equal to 1. So if you don't need to define the forgetting factor, and you recall the function just with the first 2 parameters, input parameters, lambda is assumed to be 1, which is, if you remember, the classical recursively squared. So no forgetting factor. And that is just for you if you want to follow the implementation. It's not required also for the exam, but in some cases it helps you to how to learn how an adaptive algorithm works. And the main function is the second script file, the MATLAB file, and is so it's assuming that the order of the model is 3. We are using, is not quite important, it's just an example. So the lambda is 0.7, and the function is recalling the data. So we are using a Simulink file in a while that generates the data, and it displays the changing of the parameters. So let's open Simulink, and then let's open the first parameter change. So it was used for the example of fault detection in isolation, so, but it doesn't care. It can represent the changing of the working conditions, for example, in a real process. So I'm going to explain the main points of this. So we have, well, for you is important to the generation of the data here, which is represented with the green blocks. Green blocks, as you can imagine, is the 2 space blocks in Simulink. So you are exporting the data. We are using a number of about 1,000 data. So the switching model is hidden in this system. So it just to remember you is the implementation as a difference equation of a dynamic system. The problem is that when you have changing parameters, you cannot use the block of a transfer function, because the transfer function block normally assumes that the parameters are fixed, so you cannot change it. So if you want to implement, at least in a classical way, a linear time varying system, you need to design or represent it as a difference equation, but you shouldn't care about it, because normally when you are working with the system, you already have your process. You don't need to develop, or at least if you are developing, for example, when you are working, when you are employed in a company, normally the process is the result of a teamwork. So you are, normally is not assumed that you are working alone. It's a team of experts that are work. Everybody has a specific task. So normally you assume that the process, the model of the process is already available. And is using, this is the input, so it's generating a changing parameter. So we have, as you can see here, we have a switch is the switch. It's not the manual switch, but is the input is driven by this block, the Boolean block. So when before the switching, the parameter that is changing has the value 0.2, and after the changing, the parameter has a value 0.9. So it's something quite easy to compare. And so there is also the noise. So it's something that is realistic. And if we simulate, let's see if we can see there is here is the output compared with respect to the parameter which is changing. So as you can see here, after the change, so you can see here the change is the middle of the simulation, and you can notice that there is no an abrupt change, but it's something that this parameter is changing the dynamics of the process, because before the change you see that the output is a little bit slower, and after the change is the output is changing more rapidly. So it means that dynamic, so the system is the dynamics are changing and are much more faster than the case before the change. So it can represent also the changing of a working condition. As for the, I don't know, the chemical process, something that is changing in the system. And if we want to, of course, here, but normally you don't have this plot, so you have only the output. In standard cases, what you are observing is this one. So you don't know that something is changing. Of course, because of dynamics, you know that something is modified, but you really don't know what is happening. So it's why we are using, now we can, after the generation of the data, so you are in the framework of system identification, so you have the data, and in fact in your workspace you have U and Y, so you can start with your identification process, that in this case is a recursively square. You are using the recursively square approach, and if you launch this example, this graphic, you can see that The recursive square is detecting, in fact. So the parameter, one parameter, which is modified in your system, generates the changing of all the variables in your process. So it's a little bit more complicated. So it means that, and what it noticed that you, at the beginning, or at least at the first sight, you can really understand that something is changing. Or I displayed here, I don't know if, yeah, it's better here. You can see that the evolution, the amplitude of your output is changed because it's exceeding some thresholds. Normally, so in normal conditions, or at least you can think of it as a starting working condition, and then after 500 seconds, the system is changing, and also the range of your output is modified. And so this is the implementation as a script file, but something which is more useful, in my opinion, is to understand or to see how to implement it as a block in Simulink. As is what that we are going to use in our next example. So in this, I want to explain. So in this next example, I use the same example in the previous case, and I arrange it as a subsystem in order to simplify the display and also the organization. And in this second block, and it's notice, I use the block, the recursively square estimator, which is very useful and it is easier to implement with respect to the organization or to implementation as a script file. So something that you need to remember is that you need to generate the regressors, and in this case we are using 3 regressors. So normally remembering, so in this case I'm using the pre-knowledge. If you remember when we talk about the system identification, and this can be done because we know that the system has order 3, so we know that we need a regressor of order 3, and the output is just one delay of 3 samples, and we are using this block, which is very useful because, as you can see here, we are comparing the 3 parameters that are generated by the Simulink block and in the same condition. So I'm estimating here from the block, so it's the same of the script file we saw a while ago, but is implemented as a recursively square block. So it's something very much simpler. And you can see here there is a comparison of the 3 parameters. So if you launch this program, so it's generating the parameters, is the data, is generating also the parameters, and is comparing the results of this estimation. Okay, so as you can notice here, so it's simpler to show. I use the same forgetting factor, and as you can see here, the system is able to detect, to understand. It's like a detection. It detects that there is a parameter change in the system. So it's something that can. So in yellow you have the values of the parameters in theory. So normally you don't know this change, something that is unknown, but what you can or estimate is just the variation in blue. So, but in this case, we know that there is a change in the parameters, and it's something that is very useful. So this is concludes this example. So this is a block that we are using in one of the next examples, and it will be used for the parameter estimation. So remember, when we use this block, you need to generate the regressor vector, and if you remember in the block, but is something that you can easily modify, as a design parameter, you need to include in this block the number of parameters that you are estimating, which is the same of the dimension of the regressor vector. And the sample time in this case was 1, so it's very simple. And you need to select forgetting factor and lambda. And of course, we are using the output estimation error because it's the estimation of our error. So it's something that we are using for the design of the controller. And in fact, the error is this one. You can see here that is quite small. So after a transient, you have that. It's like it can be at the first sight considered as a white process. You need to perhaps to perform some statistical analysis, but as a first sight you can see that at least you can assume that it's a white process. So it can be right. So okay, this is concluding here.